Hello, this is Andy Schweitzer, and this is a video about entropy or disorder, a series of thermodynamic videos. A few things we're going to look at today is a reaction going to be spontaneous, and that is how entropy plays a role in that. Is a reaction going to be gaining or losing disorder? Why does it matter if a reaction is gaining or losing disorder? How do I calculate the amount of disorder gained or lost? So we already talked about the fact that from a previous video that we want to know, is a reaction going to proceed spontaneously? Of course, we have the reactant concentrations and we have the product concentrations, and we want to know is, if we have our end point or our equilibrium point here, is a reaction going to proceed towards the products? This is going to involve a few factors. One is delta H, which was covered in the last video, but today it is delta S. And S, meaning entropy, is the amount of disorder. Alright, so is a reaction going to be spontaneous? Well, it turns out that in nature, well, let's just put it this way, it requires energy to create order. Okay? And by order or disorder, I mean movement. So it takes energy essentially to stop movement. And we'll see more about that in a moment. But so if you have, for example, a reaction where the substance goes from being, goes from let's say a system, okay, and the system gains order. Well, if your system gains order, or I should say loses disorder, loses entropy, then you have to enter energy into that system. It requires energy to create order. Okay, so a negative delta S, or losing disorder, okay, this is a process that requires energy. And therefore, this is a non-spontaneous factor. Okay? Meaning that it's not going to be able to do this until that energy is provided. If that energy is not available, then it just doesn't work. Whereas a positive delta S means that when a process actually creates order, if a system creates disorder, then it technically would be releasing a little energy to its surroundings. So order is energy. Alright, and therefore this is a spontaneous process. Alright, so just so you know the signs and whether that is indicating it's going to be in a spontaneous or non-spontaneous direction. So one of the other objectives says, is a reaction going to be gaining or losing disorder? We want to be able to look at a process and just actually say, okay, X going to Y, X going to Y. Okay, as I look at this, is this thing gaining disorder from X to Y or losing disorder from X to Y? So we want to simply be able to look at this thing and analyze and say, okay, just by looking at, is this thing a positive delta S or a negative delta S? Now again, entropy is simply movement. So let's look at a few qualitative things you can do to get this to work. To just look at it and say, I know if this thing is going to be increasing or decreasing in entropy. And it's nice to be able to look at something and say, okay, well, if it's increasing in entropy, then that's an indication that this thing very well could be a spontaneous process. Or if it's negative delta S, I can say, okay, well, this is something that may not happen on its own. First things first, we have solids have less entropy than liquids, which have less entropy than gases. Gases are really moving around. So in this case, we could have X solid going to X liquid, and this would be an increase in entropy. There's a bunch of little things here. Then you have another one, say let's go with temperature. As you increase in temperature, you increase movement. Okay, so anytime you increase temperature, you are going to have a positive delta S. A lot of times we deal with gases. Let's say we have X plus Y. Both of these are gases. Go to, let's say, they just form one gas particle. Okay, so in this case, you have to imagine that as we proceed to products, we go from having 2 gas particles to having one. So we have less particles. You simply add up your number of gas particles, 2 of them, versus in this side I only have 1. This would be a negative delta S. A good example of this is mostly combustion reactions, where we have, let's say, well, the reason why gases produce compression inside combustion engines is because they produce lots of particles and at high temperatures, so they're moving around very fast, lots of disorder. But anyways, you could take something like, let's say, methane, CH4 plus O2 yields CO2 plus H2O, and I balance it. 4 will be there. 2 times 2 is 4. 2 oxygens plus 2 oxygens is 2 here. So that is balanced. And notice we have 3 gas particles. Well, bad example. In this case, we got 3 particles and 3 particles. So in this case, we would not be able to indicate whether we're gaining or losing entropy based on the number of gas particles. The fact that it produces the heat energy in this case is why we're going to be getting faster moving particles and therefore more disorder. But you'd always be able to add up the number of gas particles on each side. Another thing you should be aware of is that a mixture is always more disordered than a pure substance. That would be a going from a mixture to a pure substance would be a negative delta S. You also should be aware of that entropy, unlike enthalpy, is going to be something that is have an absolute measurement. So we have a definition for a zero entropy. Zero entropy equals a perfect crystal spelling right, perfect crystal at 0 Kelvin. So anytime this will very well give you a lot of ways to look at a problem and understand whether we're gaining or losing entropy. One other one that I'll just quickly mention here is I think it's a very small amount, would be comparing ionic solids. Now, ionic solids aren't moving very much, and they're very tightly held. But you should note that when you have like NaCl versus magnesium chloride, that this is a positive 1 minus 1, positive 2 minus 1, that the difference in charge between these two individuals, it signifies the strength of the bond. and you should note that a increased strength yields lower movement. So this would have a little bit larger amount of entropy than this guy would. So lower entropy versus higher entropy, I should say backwards. The NaCl has a weaker bond, so it has a little bit higher entropy. It's a little bit lower entropy. Okay. So we want to be able to look at any kind of chemical reaction to say, is this thing gaining or losing entropy? And we'll spend a little time in class looking at this. It could be something as simple as going from H2O liquid to H2O gas. Well, in this case, gases are fast-moving particles, therefore this would be positive delta S. You could have another example where, let's say we go nitrogen triiodide. Okay, this is a solid, and therefore it goes into nitrogen gas and iodine gas. Now in this case, we have a solid going to two gas particles, gas and gas. Now it's not even balanced, but put a 2 right here, a 3 here. So this has got a very large increase in entropy. Okay. So again, we want to be able to practice that and look at, are we or are we not increasing entropy just by inspection. So is a reaction gaining or losing disorder simply by inspection. All right. We already talked about why it matters if a reaction is gaining or disorder. It has to do with whether it's going to run or not. Is it going to be spontaneous? How do I actually calculate the amount of disorder that that the actual value? Okay. Now, it's calculated the same way as, I'm going to add a new line here. How do I calculate? This is what we call a state function, which really means that it's just the product sum minus the reactant sum equals the net difference. So in this case, let's try an example. I'm going to pause this for a moment, grab my charts. You can do the same, your thermodynamic values, and we'll pause. Alright, so this is our chemical reaction. It's methanol. Now I'm just going to make it a gas, and then we will have all these guys be gases. That's the way I want to do it. So we have carbon dioxide gas and water gas. Now, just looking at this thing, I should note that they're all gases. Okay, even though the methanol very often has to go from a liquid to a gas first, but in this case, it's a gas, and I have on my reactant side five gas particles on this side, and on this side here I have 6 gas particles on this side. So I have a delta S that is going to be positive just by the fact that I'm increasing the number of particles, increasing the amount of movement. Alright, so what else do I have here? I got, I'm actually calculate these values. So what we're going to do is we're going to grab each value of the entropy, okay, and it is an absolute value, so every single individual has an entropy. It's on a per mole basis, so then I will take my values and I will multiply by the number of moles that I'm present here, so 2, 3, 2, 4. Then I will add up all the entropy on each side, and then I'll take the product entropy and I will subtract that from the reactant entropy to give me my difference in entropy. And every single state function is the same way. Delta H is a state function, delta S state function, delta G state function. They're all calculated the same way. So we'll go ahead and give one example of this. And there we go. So methanol is a gas, net, and I'm going to go to the second column, 239.81. 239. I'm just going to round it up. 239. And then the oxygen, down a little farther. O2 is 205.13. Notice that the delta G and the delta H are 0 because that's based off of formation from elements. This is not. 205, this is absolute value. Alright, 205. I have carbon dioxide gas. Find her. There we go. 213. And then we have water, gaseous, and right here, gaseous water, 188. So I have all my values, and again, some of this is just keeping track of your values and not getting too goofed up by this. So let's go through and calculate this out. 239 times 2 equals 478, 478. 205 times 3 equals 615. That one you can do in your head. This is going to be 426. 188 times 4 is 752. Add these two guys up to get the total. 478 plus 615 equals 1093. 426 plus 752 is 1178. I'm going to take my product, 1178 minus 1093 minus 1093 equals 85. So equals a positive 85, which was, as I predicted, a positive value. Now notice this is going to be the delta S is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. Delta H had an additional little delta sign there because they were going from the difference from the actual element listed to the from the formation of elements. This is not made from the formation of elements. It's simply total entropy minus total entropy. So small but little interesting detail as far as why things are the way they are. Again, I guess that's how you calculate entropy. All delta H, delta S, delta G, they're all calculated the same way using your data table charts. I would mention the fact that, of course, we have delta S and we have delta S prime. Remember that prime means it's calculated at 25 degrees Celsius. All of our charts are calculated at delta S prime. So it's hard for us to get this when it's not at prime. Thank you very much.